and how you measure and so on and so forth. So the explanation is also so complex, so that's why we are not going into it. And then we kind of like going through the breakthrough measurements, how we can do breakthrough measurements, how we can measure breakthrough things via experiments, and what we can get from breakthrough experiments. Last one is like kinetics, right? So the kinetic models we have, when we kind of have the data, how we can fit using the models we got, and what kind of information we get out of it. Okay, so these are the 4 topics which we will cover in next 2 hours. Okay, so why we have to study the thermodynamics, right? So look at these ones one by one. So what thermodynamics will give what thermodynamics will give is the following, right? So the first one is, right, what is the amount of solute that can be absorbed on a surface, right? And then second one is what state variables like temperature, pressure, or any other variables that affects this adsorption process. If it affects the adsorption process, how it affects it, positively it affects or negatively it affects, and how we can maximize the adsorption by playing with temperature or pressure or any other state variables. Okay, so the third one is how can we determine the stationary and maximum adsorbed amount. So stationary means at any given pressure, maximum means at max how much it can adsorb, right? So this information we can get through thermodynamics. So last one is, and very important one is, if the gas adsorption is happening, where exactly it is happening, right? What is the location? Whether it is happening to a specific functional group, or it is happening near the pore surface, or it is happening in the bulk. So where exactly it is happening, how we can actually recognize it. Okay, so this is because once we know where exactly the process is happening, like say for example a functional group, kind of like when we introduce a functional group, it kind of adsorbs the gas molecules, then we know that this adsorption is happening near the functional group, we can add more functional groups. So for example some groups are not good, so then we kind of like create defects by removing those and then increase the adsorption. So that is why we kind of like have to have an understanding of like where exactly this adsorption is happening. And then the next one is how much energy is required to remove these things. Once the adsorption is happened, right? So to kind of like continue with the process, we have to remove this one. So that means desorption should happen. So if desorption should happen, then how much energy we have to give it to it. So that information is also we get from the thermodynamics. Okay, so let's go one by one, right? So that is the fundamental equation which we all know. The delta G is Gibbs free energy, and then delta H is the enthalpy, T is the temperature in Kelvin, so this is always a positive number, delta S is the entropy, which are all change in entropies, right? So any process to happen, so what is the fundamental thing it has to follow is that the change in Gibbs free energy should be less than 0, then only the process will happen. That's what we kind of call instantaneous process, right? Okay, so when you look at that equation, we know that delta G is a negative number here. If adsorption has to happen, then this delta G should be negative, then only it will happen. At equilibrium, delta G is 0. Okay, so that's one first one. So next we will go one by one. So we leave about delta H. So go with T. T is a temperature which is in Kelvin, so it's always a positive number. Third one is delta S, which is entropy, change in entropy. So what is entropy? In simple words, what is entropy? Entropy talks about the randomness. So if we don't go into the fundamentals and all, in basic, entropy talks about the randomness. So what is happening in the gas adsorption? We have a surface here, and then we have gas molecules, right? So these gas molecules will come. So this is kind of like say initial configuration, and then these gas molecules will come and adsorb on the surface, right? So when you look at the S initial, that is entropy in the initial state of the gas molecules, which is in the gas state. So the randomness in the gas state is very high. So this is a very big number. right? And what about this final one? So these gas molecules will come and adsorb onto the site. So they kind of like stick to the surface. So the randomness decreases. So this is a small number compared to this one. So therefore delta S small minus big always less than 0, right? So now look at this equation. So what we have is delta H is equivalent to delta G plus T times delta S. We said that delta G is a negative number. So this is negative. This anyhow leave it, and this is negative. So the overall everything is negative. So delta H is always negative. What it means is that whenever adsorption happens, heat releases. Okay, so that's why adsorption is an exothermic process. It releases heat. So at equilibrium, what happens at equilibrium? Delta G is 0, right? So your delta H will become T times delta S. This is the equilibrium condition, right? So that's what we kind of like showed, that change in enthalpy is always negative, and therefore adsorption is an exothermic process, right? So as we said, heat always releases. So what is the challenge with heat release is that yesterday we kind of like have discussed that when the temperature increases, adsorption decreases, right? That we discussed in terms of Le Chatelier principle, right? Now what we are saying is that we have a solid surface and a gas molecule comes and adsorbs and heat releases. So what happens to this heat? It has to dissipate, right? So some amount of heat will So when a gas molecule comes and sit onto the surface, so the heat releases. That's what we kind of like discuss. And this heat will be absorbed by the solid, maybe part of it, and part will be dissipated to the surroundings. Right? So we never know what happens. So it may be like all the heat will be kind of like dissipated to the surroundings, or all heat may be kind of like absorbed by the solid, or it may be partly divided between these two. So whenever it kind of like goes everything into the surroundings, we don't have any problem. But the challenge comes in the other way around, when all the heat releases is absorbed by the solid. So the temperature of the solid increases. So it is not good for the adsorption. So the desorption starts. Right? So that's why we have to have like always look into the adsorption and the heat of adsorption, because if the heat of adsorption is pretty high, so it actually favors the desorption. Okay. So that's why we every time what we do is we kind of like try to calculate the heat of adsorption and see it is very high or very low, right? So and then what we can kind of like inference from the heat of adsorption, that's what we will do, right? So you can see, read it. So adsorption is the exothermic process, and therefore energy is released during this process of adsorption. That's all good. Measurement of the heat of adsorption of the specific gas onto material is then very important consideration, and it actually gives knowledge of the surface area and porosity of the material. So why it is that if you have more surface area, it can absorb more gas molecules. If it absorbs more gas molecules, it will release more heat. Right? So based on the heat of adsorption from the process, we can understand the surface area and the porosity of the material, right? So that's why this is also like one way to look into it. Okay. So then the third one, heat of adsorption, is also indicates the measure of measure of strength of interaction between the gas and the solid. So if the gas and solid interacts really well, so it releases more heat, right? So delta H talks about the strength of the interaction. If the interaction is very less, it releases less. So even that also kind of like gives one information. So in all, the heat of adsorption is a fundamental thermodynamic feature, and its value can be utilized practically when developing and assessing the material. So that is the reason why we kind of like try to extract the heat of adsorption. So there are several ways, like there are several definitions of heats of adsorption, like differential heat of adsorption, isosteric heats of adsorption, enthalpy of adsorption, and so on and so forth. But we fundamentally don't go into everything. We will only focus on isosteric heat of adsorption. Oh yeah, okay. Before going to that, you can see some of the materials, right? So here what we have is the list of materials like zeolites, MOFs, and silica gel. What we see is that what is the heat of adsorption. So typically for zeolites, the heat of adsorption is pretty high. So when the heat of adsorption is very high, the problem is that heat or the temperature. So that's why it's kind of like a very hard. So MOFs, so moderate, so we kind of like tunable for efficient cycling. So that means that when adsorption happens, we have to desorb it and then again restart the process. So in that sake, MOFs are good. It will have more cycling efficiency. And then silica gel has a very low heat of adsorption. So it's easy for desorption, therefore good for cooling. Okay, let's go. So among all heats of adsorption, specifically we focus on isosteric heat of adsorption. So this is also called differential enthalpy of adsorption. This is because it actually talks about the change in enthalpy of adsorbate when we add a small amount of gas molecules into the system, right? So this is the definition how we get it. It's ratio of infinitesimal change in the adsorbate enthalpy, that means the solid enthalpy, to the infinitesimal change in the amount adsorbed. Like when we have a solid, so some gas molecules are already adsorbed, so which has an enthalpy of some H, and then you add like a small amount of gas molecules, then calculate the H2. What we get is what is the change in enthalpy when we add small amount of this one, right? It goes here. Okay. So similarly, higher the isosteric heat of adsorption, it means stronger interaction between the adsorbate and adsorbent, leading to higher adsorption capacity, but harder for the desorption, which we already discussed. And then lower isosteric heat of adsorption means weaker interactions, making desorption easier, but reducing adsorption capacity. So we try to kind of like have to manage these two things. So the isosteric heat of adsorption cannot be like higher or cannot be lower. So we kind of like always have to play around with these values. Okay. So like what usually we observe, like we will not observe like same for all the cases, but in general cases how we observe like isosteric heat of adsorption. So in homogeneous adsorbents, right? So isosteric heats of adsorption remains constant at low loading, right? That means that at very low pressures, isosteric heat of adsorption is kind of like constant with respect to the loading, and then it kind of like increases, right? So with increase in the loading. So that means that isosteric heat of adsorption is not same with at all loadings. That means that low loading means that, so how do you calculate the isosteric heat of adsorption? Say for example, we have only one gas molecule adsorbed onto the surface, right? So that is our H1. Then you add one more molecule, calculate H2, and then this delta H will give you at low loading. But the same measurement can be done at high loading. That means that low loading means that, so how do you calculate the isosteric heat of adsorption? Say for example, we have only one gas molecule adsorbed onto the surface, right? So that is our H1. Then you add one more molecule, calculate H2, and then this delta H will give you at low loading. But the same measurement can be done at high loading. That means that in the initial stage itself you have like hundreds of molecules, right? So that is our new H1. Now you try to add one more molecule here. So then calculate H2. So this will give you new delta H. So that means isosteric heat of adsorption depends on the loading. Okay. That is for homogeneous. Usually whenever we have a homogeneous surfaces, this kind of behavior we observe. This will be something like this. Say if we plot, so this is isosteric heat of adsorption and this is with the loading. So usually at low loadings it is constant, and then so may increase something like this. So that is for homogeneous surface, that's what we say. And a different behavior is observed for heterogeneous adsorbents. That means that the surface characteristics of the adsorbent is heterogeneous, right? So that time isosteric heats of adsorption decreases with the loading, and it's kind of like goes something like this. Okay. So at the end of the day, the point I would like to highlight is that isosteric heat of adsorption does not kind of like follow a same trend in all the materials. It depends on the material to material and gas to gas. So it may kind of like constant, increase or decrease. Okay. So that is the only point you have to learn here. Good. How we kind of like measure it, right? So experimentally we can do by two ways. One is kind of like from calorimetric measurements, like you add the adsorption, like you add like few amounts of gas molecule and see the increase in temperature and then calculate back. Otherwise we can actually calculate from the adsorption isotherms, right? What we have to do here is that, I think I have somewhere. So we will use Clapeyron equation. So that's the Clapeyron equation. So we can use the Clapeyron equation to compute it. So what we have there is isosteric heat of adsorption is equivalent to RT square dou ln P over dou T at any given loading Q, right? So this we can write it as R maybe. Right. So because here we have T square dou T, so that I can written as dou of 1 over T. So 1 over T is like minus T square, so this comes here. So it's like minus something. So what we can do is that at any given loading, right? This says that's a given loading. So first we try to extract the adsorption isotherms, which is the function of pressure versus the amount adsorbed Q at different temperatures. So for example, this is at one temperature T1, this is another temperature T2, sorry, it all should start from here, okay. And it is at another temperature T3. So first we have to do is that we kind of like try to extract the adsorption isotherms. What we need is that change in pressure with respect to change in temperature at any given loading. So that means that first you fix the loading. So any loading you take, okay, and then so read the say P1, P2, P3. So at any given loading Q, what we have is P1 versus T1, P2 versus T2, P3 versus T3. So we have these data points. What we can do is that we can actually plot 1 over T versus logarithm of P So they must follow a straight line like this. So because we have 3 points here, so just like put it here, somewhere here, connect it. What we want is dou ln p over dou t. That means that's the slope of this one. And multiply with r, we'll get the isosteric heat of adsorption. So this is another way without going for calorimetric measurements. When we have the isotherm data, we can do this one. Okay. Yeah. So this is the one you can see. So what here you have in addition to this one is that, right, you have at different Qs. So that means that this corresponds to one Q here, as you see. So similarly at another Q, and then you can actually plot it. You can see that in this case, all are like parallel. That means the slopes are same. So that means that isosteric heats of adsorption is constant with respect to the loading. Okay. So how we will do same thing from the simulations, right? So we kind of like use the fluctuation formula. So what you see here is that the brackets here kind of like talks about the ensemble average. We kind of like, it means that we take like different ensembles. That means that different configurations of the same structure, and then calculate the, so this n is the number of molecules in the system. That means when you are trying to do the gas adsorption, you try to insert a molecule, then try to count how many molecules are there in the system. U is the total potential energy of the system. And then, so only 2 terms are there, and Kt is the, K is Boltzmann constant and T is the temperature, right? So like this, through GCMC simulations, we can calculate the isosteric heat of adsorption, right? So look at this one. This is the example, right? So what we see here in the yellow one is with the Clashes-Clapeyron equation. That means from the experiments, what they have done is they calculated the adsorption isotherms and try to get the isosteric heat of adsorption. And then here 295, 300 and 305 at different temperatures, the isosteric heats of adsorptions were calculated using the fluctuation formula from the simulations. So you can see they are all very well in line. So this is heat of adsorption in 1 geolite, which we kind of like discussed, which is around 40 kilojoules per mole. Okay. And what else? Yeah. So this is isosteric heats of adsorption in different MOFs, which is calculated using simulations again, right? You can see one interesting thing here. This is CO2 adsorption in different geolites. So the first one, you can all see that on the left hand side, what we have is the adsorption isotherm. So these adsorption isotherms in 3 different MOFs have 3 different characteristics. You can see this one, the one in green and then one in red, like which is GIF 8 and MOF 74. They follow Langmuir kind of adsorption isotherms. That means type 1 adsorption isotherms, you can see clearly. But however, if you see the MOF 5, which is in the blue, it follows type 2 kind of adsorption isotherm, right? It's kind of like going and then going. So here it's like monolayer adsorption is happening, here multi-layer adsorption is happening. And with respect to the adsorption characteristics, you can see that in these 2 cases, right? So like especially in the red one and the green one, like you see the amount adsorbed is pretty low, but it's always increasing. A slight increase, I cannot say, but especially when you see the third one for MOF 5, it's like a sharp increase is observed. So even you say like all 3 are MOFs, but you can see 3 different characteristics here. Here in the first case, isosteric heats of adsorption is almost constant at 30. In the second case, it's kind of like going from 17 to 25, and in third case, 15 to 30. So again, as we kind of like discussed, isosteric heats of adsorption depends on the system as well as the type of the gas molecules. Okay. But it is very interesting to kind of like extract all this data from the simulations, especially this course is for like based on the simulations. Even before we go for the experiments, we try to run the simulations and see the isosteric heat of adsorption and then understand whether this actually makes sense or not before synthesizing any material. Okay. However, as we kind of like also discussed, the force fields is a challenge. So we have to kind of like validate the force field before going for these kind of calculations. So these are very simple calculations anyone can do on any system. You can try using GCMC whenever you got the time. Okay. So these are all do with the isosteric heats of adsorption. So the second one we talk about the diffusion, right? So far we kind of like talk about the isotherms, thermodynamics, how to extract the isotherms, what information we can get out of the isotherms, and so on and so forth. That means everything to do with the equilibria. So the second one which we also important in the adsorption is the kinetics, right? So maybe we can say that, so you can try to kind of like do all the adsorption equilibrium things and then say that, okay, this material is good for the adsorption. So, but if we don't kind of like consider the kinetics, so how it will affect? So that's what we will see now, right? Why the kinetics is important. So that's what we kind of like discuss in this part. So whenever you see the practical solids in the industries, they are porous, and then overall adsorption rate depends, especially it's kind of like controlled by the diffusion inside the particles, right? That means that even it can accommodate more number of molecules, even it can adsorb strongly, but the thing is that if the diffusion is slow, it will take long time to reach the equilibrium. So then the adsorption becomes very slow process. Most of the time it will be the rate limiting step. Adsorption is like usually a spontaneous process. So it happens very quickly. As we discussed, whenever we have a pore structure like this, so here if the molecule is diffusing pretty slow, then it will take long time to reach the end of this one, right? So it slowly happens. So then what happens is that when you try to kind of like get time versus adsorption data, it happens very slowly. Happens like that. So that means that to run an adsorption process, you need a very long time, right? So that's why even equilibria is important. The equally important thing is the kinetics, right? So how the diffusion process occurs inside and so on and so forth, that's what we will look into it. Even before going to that, like, so the pore surfaces and all is more complex. Before going to that, we kind of like, let's see first what kind of like diffusion occurs in a cylindrical capillary. So that means that we are not considering any pores. We just consider a diffusion is happening in a cylindrical pore. So something like this. So assuming we have a cylindrical pore like this, and a gas diffusion is happening through this. So as simple as this one. So these are the several mechanisms that can happen, right? So what is Knudsen diffusion? So that means that, okay, so it's kind of like it can go through like all these things. So one is Knudsen diffusion, which we will kind of like discuss one by one, then viscous flow, then continuum diffusion, and then surface diffusion. So the gas molecules can go from here to here using any of these four mechanisms. Okay, so we'll see what these mechanisms actually contribute. We'll see, come back this one later. So this is the Knudsen diffusion, right? So Knudsen diffusion kind of like happens when the gas solid collisions are important. That means that when the gas molecule that enters is kind of like colliding with the wall, going back. Right? So that's what Knudsen or free molecule flow is, where the gas molecules collide more frequently with the walls of the container rather than colliding with themselves, like with other gas molecules. Okay? So here the gas composition is not important because gas-gas collisions are not important. What is important is the gas-solid collisions. Okay? So this usually happens at very low pressures. That means when we have very low number of gas molecules, these gas molecules will try to go and then collide with the solid walls, and then the diffusion happens. Okay? So to happen, the driving force for this process is still concentration gradient only. So why the gas molecule will go from here to here? Because of the concentration gradient. Because of the concentration gradient, it wants to go from here to here, but while going for that, it actually going through Knudsen diffusion. Okay? So here what we kind of like characterize this one by Knudsen diffusivity. So we calculate the Knudsen diffusivity, and then we kind of like see this. And from this process, what can happen is that because the solid wall collisions are very important, so the separation can happen. That means that some molecules may collide with the wall more number of times compared to the other molecules. So they can actually, like, some molecules may move faster, some may move slower. So then the separation can happen through Knudsen diffusion. Okay. Okay. So we kind of like talked about the cylindrical pore. But what about our geolites or MOFs? They don't have cylindrical pores. They have different pores. So what happens there? Right? So that is a complex process, because usually we cannot characterize the pores of a geolite or MOF, like how exactly it looks like. But what we kind of like can see is that what can happen when a molecule collides with the wall, right? So for example, here we have a solid surface, and then a molecule will come and then collide with the wall. It can go in any direction. Sorry. Right? So this is called diffusive reflection. That means that for all these things, it has equal probability. We never know where it will go. Okay? But however, when the surface is pretty smooth, like what you see in a carbon nanotube, right? Carbon nanotube is kind of like almost close to the perfect surface, right? So then what happens is that most likely the gas molecule which kind of like collides with the wall will reflect back with the same angle of incidence. Say for example, it comes with an angle theta, it will also go with theta. If it comes with velocity vi or momentum, whatever, it also leave with the same velocity. It will not lose the velocity, it will not change the direction. So the angle of incidence is equivalent to angle of reflection, and then velocity will be conserved or momentum will be conserved. Right? So that's why whenever we see the diffusion in carbon nanotubes, they are like 2 to 3 orders more than compared to geolites or MOFs or so on and so forth. What you see in carbon nanotubes, the diffusivities are in the order of 10 power 4 or 10 power minus 3 meter per second. But when you see geolites or MOFs, it all depends upon 10 power 6 to 8. Anyhow, that's still questionable, but yeah. So they are in the order of 10 power minus 6 to minus 8. This is because this is the reason. So the collisions in a smooth tube is most likely to be a specular collision. So it comes like that, what you can see there. But whenever we see a geolite which has a structure like this, which is like not, surface is not uniform, right? So where it hits the wall matters. So for example, it hits the wall here, it will come back most likely. If it hits the wall somewhere here, it will go back like this. So the pore characteristics is very important to understand the diffusion in geolites. So that's why the pore surface we have to analyze before understanding the gas diffusion in geolites and MOFs. Okay. Right. So the second mechanism is viscous flow. So this is nothing to do with anything. This is just because of the pressure gradient. So it will act same on all the molecules, right? It's just like flow is happening. All the molecules will flow with the flow. So we don't have any control on this one. So the driving force here is the total pressure gradient actually. And how we characterize this one is the viscosity. Only viscosity matters when the pressure, because the pressure gradient is same. The viscous fluids will go slower, like slightly less viscous fluids will go faster. So the only parameter that characterizes the viscous flow is the viscosity. Okay. So here no separation will happen because all the species will go with the same flow. Okay. So the next one, which is very important one, is the continuum diffusion, right? So the continuum diffusion is actually kind of like opposite to what we kind of learned in the Knudsen diffusion. Knudsen diffusion is when gas molecules are colliding with the solid, whereas the continuum diffusion is happening between the collisions between different species. That means that it's still pores only. You have this is gas 1 and we have gas 2, right? So we are trying to separate these two gases. So then, right, you have G1, you have G1. I wish we have one more. All are black only. Okay. So the continuum diffusion is characterized by the collision between gases of different types, not of the same type. Okay. So this usually happens at higher loadings because at higher loadings we have more number of gas molecules. So they try to collide with each other rather than colliding with the walls. Okay. So different species move relative to each other, and then binary diffusion coefficient is the one which we kind of like characterize. So when we write the fixed equation, which is the flux, which we write like this. That is the flux, and then J2 is the flux of the second component, which is characterized by diffusion coefficient of 2, 1. It is density by 2J. So here the binary diffusion coefficients will come into picture. So we have like so many formulations like Maxwell-Stephen formulation, Lagrangian formulation, and so on and so forth, but because we are not dealing mixtures in this course, so we are not talking about that framework. And discussing these frameworks itself is 1 hour lecture, so we don't kind of like go into this, but just remember this is the fixed equation. So that's the flux is equivalent to d12 dou c1 over dou z. That's the flux of the second component, which is going d21 minus dou c22. And this d12 d21 is called binary diffusion coefficients, which dij, which is. And the factors that affect here is the total pressure. Loading means loading of the molecules, and the temperature, right? So higher the temperature, it will have higher energy, so it will most likely collide with other gas molecules most frequently. So similarly the pressure, when the pressure is higher, so it will try to be close with each other and then collide with each other. Nice. So the last one is the surface diffusion, which is more complicated and very important to understand in terms of the adsorption. So this happens inside, but not like Knudsen diffusion. So there are several mechanisms that people have been proposed, but we usually go with 1 or 2. So the first one, usually we kind of like talk about only one now because of the time one. So once the gas molecules enters into the pore, right? So this is assume like a geolite pore. The gas molecule adsorbed at one site, and it want to go to the second site, which is here. So in Knudsen diffusion, what happens? The molecule will come and collide with the walls and go like this, right? So in surface diffusion, what happens is that it will not go like this. It will just jump from one side to the another side like this, right? So what it will do, it will first sit here and it will wait until it get the energy that kind of like required to jump from here to here, and then jump from here to here, jump from here to here. So this is what we call it as surface diffusion, because the diffusion is just happening on the surface from one side to the another side. Oops. Think something. Yeah.
So what force is bending the path of that?
No. This one we like. You mean to say how it is going like this? Why not like this? That's what. No. This is kind of like what we are saying is in terms of the activation barriers, right? So, for example, when we try to get the free energy profiles, right, on the surface, what is usually here is, so here it will have very low free energy, that's right. Then the free energy kind of like very high, so it will not like go in this path. So it's kind of like go to a free energy where it is more like, so that's kind of like corresponding to the barrier kind of stuff. So it prefers to go to a place where it has to kind of like it experiences low resistance and then go back to again to the adsorption site. So that's the free energy related stuff. Yeah. Right. So in the overall thing, we kind of like have different stuffs like diffusion barriers, like what happens in a system, assuming this is kind of like a pore there. So right, so here we have the pores, right? So generally, because of the chemical potential gradient, the gas is moving from one side to the other side. Then we kind of like try to understand what kind of barriers can exist. So the first thing is that on the feed side, so the gas molecules are like moving in the gas side. So there will be an external resistance that like gas molecules have to move, and that will be like you can ignore it. So usually gas molecules experience very low resistance, and that's why the diffusions are very high. So the second one is that when the gas molecules try to enter onto the surface, right? So you have a pore here, right? Something like this you have there. So the gas molecules, the reservoir is here. So that means you are sending gas molecules. So gas molecules are coming. It's not that all the gas molecules will come and enter into the system directly. Some gas molecules will come and hit at the surface. So then it will try to kind of like move on the surface like this or like this until it enters into the system. So this one we call it as surface barriers. That means that the gas molecules that has to experience some resistance to enter into the system. It is not same for all the molecules. Say for example, this molecule, maybe lucky molecule, will kindly directly enter into here and it does not experience any surface barrier. So this may be a poor one. So it go and hit here and then it will kind of like roam around. Sometimes it may go back here and come back and do whatever it wants and then enter into the system, right? So the extra path it has to travel. So that kind of like we also need to consider the resistance there. That's what the resistance we kind of like to see. Once it enters into the system, like somewhere here, so then it has to kind of like diffuse through it, right, from one place to another place. So this is either we call it as surface diffusion or like depends on the kind of diffusion it happens. It's also called intracrystalline diffusion. That means within the crystalline thing it diffuses. So it's called intracrystalline diffusion. And then it has to dissolve, right, if I want to go back. So therefore these gas molecules have to kind of like experiences these many resistance before reaching the end of the pore. Okay, so this is an ideal case, right? Whatever we are talking is an ideal case. That means that okay, there is a surface here. Even whenever we say it has a pore network something like this, but still it's an ideal case. That means that whenever we say like okay, this is my energy landscape, so that means ideal things are there. But when you kind of like try to synthesize a material, it will have a lot of defects, right? So these defects will again affect this diffusion process. So look at those ones. So whenever we kind of like try to see, there will be so many structural defects. That means that, so maybe you have a pore like this, say something like this, while synthesizing the crystal like a geolite crystal, right? A defect formed in such a way that some of the pore is closed, right? So it, when we kind of like try to compute all the diffusivities, everything based on the ideal structures, what you will get is the ideal case. But in reality what may have is that, so there may be defect at the entrance, there may be defect in between, and then you see where we kind of like considered sometimes what here they considered is that these gas molecules kind of like, see there is a defect there. So the gas molecules cannot go there. It enters, because it cannot travel, it has to come back and go, right? So these are all the extra resistances it has to kind of like experience because of the defects inside. So there can be grain boundaries, because when we have like more grains, so the boundaries can create a lot of defects. Intergrowth can be one kind of like defect. And then surface barriers, what you can see here is that, I will not go through everything, but what you can see here is that the gas molecules that enter into the system, here you see at the surface, the forces experienced by the gas molecule is very different. Say for example, so you consider two gas molecules, one is exactly at the center of the crystal, so it experiences forces from all the directions because it has, right, something like this. But what about the one molecule that is exactly at the entrance? So one side it has the crystal, another side it has all the gas bulk reservoir. So the forces that is acting from this side is quite different from this side, right? So this molecule behaves differently than this molecule. So those are the things which we kind of like have to consider whenever we kind of like try to model things. Because when we kind of like model using simulation softwares, what we do is ideal case. That means that we kind of like consider everything else is perfect, but which is not the case. That's why whenever we kind of like try to compare the experimental data with the simulations, we kind of like, most of the times we may not able to match it, and we kind of like question the force fields and others, so on and so forth. But at the same time we also have to consider that there will be so many defects and so many other factors that actually influence the simulation results. And usually in experimentation what people do is that they don't care, because of the fact that what they are seeing is the actual one, right? So when they kind of like try to synthesize a material and try to prepare a membrane, they say like okay, this is my membrane, and then they will just run an experiment and try to see how it is performing. But they will never kind of like thought like okay, what exactly happening inside, so why it kind of like changed like this, why it kind of changed like that. They don't care, because that is an actual thing. But when we kind of like try to model it, right, because we are not doing the actual one, we are trying to mimic the actual one, so we also have to consider everything like this into the system, right? And yeah, so these are something similar like this. It's an extreme case where you kind of like see a gas molecule adsorb and travel till the end, and where it found that all the pores are blocked at the end, right? You see the gas molecule enters from here, it kind of like put all the efforts to come here, but it wants to dissolve, but this block is pore, this pore is blocked. So This is one kind of like situation, like people kind of like try to model and see how it kind of affects the diffusion, because these molecules have to travel additional path to locate the pore which is open, right? So what people has done is this, right? So they kind of like first try to compare, like first perform the experimentation, get the diffusivities, and then perform the simulations in two experiments. One end is no defect at all, another end is like full 100% is like fully blocked, and then try to get the diffusivities in both the cases, and then they kind of like try to see how much percentage of pores are blocked in experimental setup. It's kind of like you go back and see. Okay, oh my god, we are running late, but so these are the diffusivities that we try to compute from simulations. The first one is self diffusivity, right? What we try to do in self diffusivity is that you have a pore this, and then you have like 10 molecules which is diffusing through this pore. We kind of like tag each molecule with one number, right? So then try to compute the mean square diffusement of each particle. So that means that with respect to time, how much the first particle traveled, how much second particle traveled, how much third, fourth, fifth, and then, right? So you calculate the mean square mean square displacement. That means that, so Ri of t minus Ri of 0. That means from time t is equivalent to 0 to time is equivalent to t, how much it traveled squared. So that is mean square displacement. Okay, so we kind of like try to get at time 0. So we kind of like get 1, 2, 3, how many? 5 particles are there. So we try to kind of like get the mean square displacement of each particle. This is x, this is y, like x1, x2, x3, x4, x5. So this is mean square displacement of particle 1, this is mean square displacement of particle 2, like that. And then at the end what we do is average of all these things. So that's average of x1, x2, x3, x4, x5. Like that we try to at time 0 this much, 1, 2, 3, 4, 5, like that. We get all these things and get the average and try to plot time versus mean square displacement plot, which is like this. So we have time on the x-axis. So this is average mean square displacement. It does not correspond to any particle. It is average of all the particles in the system. For long time, if you run a simulation like this, it will be a straight line. So which the slope, right? So from the slope, you can get right, 6 times, right? 6 times d, right? So from this we can calculate the self diffusivity. So this is one way to calculate the diffusivity. The second one is the corrected diffusivity. Here what we will do is we will not kind of like monitor each molecule, but we will try to monitor the center of mass of all the molecules together. So it's kind of like 1, 2, 3, 4, 5. Then we kind of like center of mass somewhere here. And then after some time, maybe center of mass is here. After some time, center of mass is here. So calculate the center of mass of this one with respect to the time. So we have only one. So that we kind of like try to plot it, which will give you the d naught. Okay. At very low loadings, both will give you the same answers. At high loadings, what happens is that self-diffusivity decreases with respect to the loading. So as the loading increases, self-diffusivity decreases, but most likely corrected diffusivity, which we call d naught, by tracking the center of mass of all the particles together, usually be kind of like will not be affected by the loading. So that means that where you are running, at what pressure, it does not matter. So the last one is the transport diffusivity. So which talks about based on the fact that we need to calculate the D naught value, which is the corrected diffusivity, times a thermodynamic factor, which will come from the adsorption isotherms. So in adsorption isotherm, what we have is the pressure versus concentration. So that means the amount loading. So using that factor, we can actually calculate the transport diffusivity, which can be compared with the experimental data. Okay. So these are the different diffusivities which we can get from the simulations. So any questions?
Also, you have mentioned MOF, methodology. What is MOF 5, NG, MOF 74? What are the differences?
In terms of pore structure. Yeah.
5 and 74?
No, they are numbers, right? What numbers you are referring to is like, so whenever people kind of like come up with a new material, so they will give the numbers. So not all the times numbers have a meaning. So yeah. Geolytic imidazole framework. Yeah. So that is also a kind of like MOF. Yeah.
One question, like what is the pressure, desirable pressure required for operating these MOFs?
You mean to say pressure difference, how much you want to, usually
Yeah, for the sake of absorption.
adsorption.
What is the pressure I have to maintain?
No, that depends, right? As I said, the amount, like what you're interested in, amount of adsorbed, right? So yeah, so amount adsorbed depends on different MOFs, right? As you see, some MOFs will adsorb, like follows type 1 adsorption, some follows type 2. So when it follows type 1, low pressure will be sufficient. When it follows type 2, we have to go for higher pressures. So we kind of like have to go for it. So there is no like single rule that kind of like says, okay, for all MOFs we have to go like this. So it depends on the type of MOF. It also depends on the type of gas molecules.
So for absorbing CO2, which MOF is better?
I think so far people are using GIF8 and GIF74 is good. That's what, yeah, people have reported simulations and experimentally. But I don't think MOFs are in a good shape to kind of like go for industrialization, because these MOFs are highly crystalline materials. So preparing membranes based on these MOFs is not so easy. So people are still working how to kind of like make it at industrial level. Yeah. So yeah.
Do you know for absorption?
COF 20.
In collaboration with the past, the cement plant. So this is the closest to a MOF industrial application we have till date.
Till date. Yeah, but like, so that's what we have some flexibility with COF, like because there is no metal inside. Uh, but still the the challenge with COFs is that the COFs will have like bigger pores.
Uh,
Oh, CALF20. Okay. Yeah.
yes,
Okay. Okay, Rajan. Okay, yeah.
so they recently discovered this material called
Okay.
20. That is a metal organic framework. Yes, they
Yeah.
tested experimentally and also the computationally. Yeah, now they are trying to scale up
Scale up.
at
Yeah.
the University of Hull.
Did they scale up?
Yeah, they are currently testing on real flue gas.
Okay.
Yes. Yes.
Any idea regarding the operating pressure and temperature they are maintaining?
But you can see his papers, very recent papers. Get to it,
Yeah.
my computer. Professor Arvind Rajan.
Arvind Rajendra. Yeah.
One MOF 74 medicine group has actually shown that in presence of moisture corresponding to atmosphere cyclically, the dynamic capacity decreases in presence of moisture by some 8 to 10%. But over the 100 cycles or so, the performance is
Stable.
MOF 74
for-
nickel.
Okay.
Yes.
Yeah.
So there is one question from online participant. How would diffusion change if there is a concentration gradient? I
There is a concentration gradient.
yes.
Yeah, yeah. So obviously the flux, right? The flux J right, whatever you write it. So what we kind of like considered when we write the flux is that the flux is directly proportional to the change in concentration gradient, and we kind of like assume that this concentration will not affect the diffusivity. But it will not be the case anyhow, but diffusivity is a function of concentration. And it's kind of like most likely the diffusivity decreases with respect to the concentration. But there are some studies where I kind of like show that diffusivity kind of like increases with respect to the concentration, but in most of the cases it decreases. Yeah. So any questions, Sridhar? Any other questions? Yeah. Yes.
That actually, is it applicable for ionic motions within the matrix?
Ionic motion within the
Matrix, the solvent matrix actually.
okay.
So, can we use it
With the ionic with ions? Yes. Yes. You may be referring to lithium ion, right? So yes, it can be. We can use it for lithium ions. Yeah.
this isosteric heats of absorption?
Isosteric heat absorption.
Maybe it depends upon the amount of absorbed materials. I have seen on the graph in which it was shown that the MOF it's absorbing more things. For the PS, let's say, isosteric heat also very less. What's the reason for that?
Isosteric heat of absorption.
Other fluid,
Yeah, it can absorb more, but it also depends on the interaction between the gas and the solid. So how strong the interactions. So if the interaction is very high, like what you see in geolites, like silicon and oxygen together, so there the interactions are pretty high compared to the MOFs. So yeah, here less interactions. Yeah.
one material is there, so activated carbon.
Activated carbon, that is very less, like the carbon only related stuff, right? So
That will depends upon the area of the surface area.
Oh no, we are not talking about the surface area and all. We are just talking about like given the material, how much heat it kind of like releases in terms of isosteric heat absorption. Yeah, and some.
Point is what I'm thinking when you are talking about temperature or heat and trying to correlate with absorption. Since temperature is same, for example, say the room temperature. Gas is near the room temperature, and you wanted to separate mixture of gases from CO2 from other gases and other things. Temperature keeping temperature the same temperature. Material or surface material also same temperature. How the temperature is increased the temperature absorb.
No, when the gas molecule absorbs onto the surface, right, it releases the heat.
Considering the same temperature of the gas, medium, and the surface material.
Right.
Same temperature. When it's getting absorbed, how the temperature will increase of that part.
No, okay. So before because of the attraction energy, right? So when the gas molecules come and sit onto the surface, right? So the heat will be released because of the interaction between the gas molecules with the surface. So that's the kind of like the what you call is the driving force for the gas molecules to come and sit onto the surface. Why a gas molecule will come and sit onto the surface? Because it is kind of like attracted towards the surface. When it comes and sits on the surface, it kind of like releases the heat. So that heat has to dissipate. So anything? No, that can be. Yeah, that can be measured like different techniques like calorimeters we have, and or else we can measure from the adsorption isotops. That's the two ways we have.